Okay,
We should ask him on that.
so here's how,
No, just that.
No, that
they might need their airplane back. Throw the airplane out. Okay.
Just leave it in the trash.
So here's how I view situations like this. Is that I'll ask you, hey, does anybody have any questions? And then that's how I use that as like a learning opportunity to go, hey, let's clarify some misconceptions, things like that. So let's start off by talking about number 29 out of the book, like that, okay? Which also was relevant to problem number 15, okay? So let's start with number 29, because if you can figure out 29, you can figure out 15. So here's the problem with number 29. All you're told is that a car has velocity v, and it stops in a distance d. That's all you got. That's all you got. And then it's going to go, well, what's going to happen to that stopping distance if we double the velocity to 2v, and then what's going to be the impact on the distance? So let's start with this idea. What variable do you not have? Time. Okay? You don't have time. So right away, when you don't have time, that equation. Okay? So we're going to look at v squared equals v naught squared plus 2ax, or 2ad, however you want to put it. Okay? Now, here's the story. What else are you told in the problem? What do you know about the accelerations? They're the same. Okay? They're both going to have the same accelerations. So if you were to draw this, you don't have to, but this also plays out to number 15. If you were to draw this on a velocity time graph, so here's the first car. It's traveling at velocity v, and it's going to come to a stop. I don't know what the time is. I don't care what the time is. I'm just worried about the shape of this thing. Okay? Now, if you're going 2v, you're going to start up here. But you're going to have the same acceleration. So what do you know about the slope of that line?
It's the same.
It's going to be the same. The two lines are going to be parallel because they're going to have the same acceleration, right? So this line is going to be parallel with that, and you're going to end up out something like this. Okay? Now, clearly, if you just have this graph, which car is going to travel a greater distance before it stops? V or 2v?
2v.
How do you know? Just looking at the graph.
The line is longer than.
Well, what does this area on a velocity time graph give you?
Acceleration.
No, the area.
Oh, what's it called?
It rhymes with displacement.
Yeah, displacement.
Displacement. So the 2v line has a much bigger area than the 1v line does. Now, here's what you're tempted to do. You're tempted to go, well, if we're going twice as fast, it should take twice the distance to stop. Okay? Straight linear relationship. Twice as fast, twice the distance. Okay? It's a possibility. I'm not saying it's right. I'm just saying you're tempted to think that, and I don't recommend that you do. And here's the reason why. So, if you were to look at this in terms of distance, and you were to solve, so you have v squared equals v naught squared plus 2ad. Okay? If you were to solve that for distance, what would that look like? V squared minus
V naught squared.
all over, it's going to equal d. In both situations, what's the final velocity going to be? 0, because they're both going to come to a stop, right? So here's the mathematical trick that you can do. This is going to represent the stopping distance of the initial velocity of v, okay? So if that's the initial stopping distance, and we're going to have the same acceleration, what's going to change is the final velocity going to change? No, because the final velocity is still going to be 0. So the v squared is going to stay the same. But I'm going to double my initial velocity. So how am I going to do that?
2 v naught.
2v naught, or not 2v naught, in this case I 2v naught. But not only do I 2v naught, I square 2v naught. You can test this, okay? All over
2a.
2a. So if this, it represents the stopping distance d, but when you square 2v naught, you get
4.
So if this side goes up by a factor of 4, what's going to happen to this distance?
Factor of 4.
It's going to go up by a factor of 4. Okay? If you were to triple the velocity, what would happen to the stopping distance?
Factor of 9.
Go up by a factor of 9. Okay? Makes sense. Okay. Now, we're going to roll that same idea into number 15. Okay, the ones that I typed up. So number 15, you've got a car traveling at 20.0 kilometers per hour. What's the first thing you're going to have to do with kilometers per hour?
Convert to meters per second.
Convert them to meters per second. Keep the same number of digits, if not more. Okay? So the first thing you want to calculate is the acceleration on number 15. What do you not have? What variable is missing on 15? Time. What are you going to use? That equation. So you're going to go, oh, a equals v squared minus v naught squared over 2d. Okay? So that acceleration, this is an ish. Okay? Because if your acceleration is wrong, everything else is going to be a train wreck. So on 15, on that acceleration, that should be around negative 5 meters per second squared. Okay? It's an ish, but it's going to be something around there. Because if that acceleration is wrong, everything is going to be wrong. Now, so let me kind of show you what I'm looking for. So on 15, I'm going to tell you, draw the motion diagram showing two velocity vectors and an acceleration vector. So all you have to do is come in here and draw V1. Now, you have only two choices. Either V2 gets bigger or V2 gets smaller. What's going to happen?
So you're smaller.
Why?
Because it's going to the stop.
You're slowing down. So then all you have to do is draw V2. Here's the next question. Which direction are your acceleration vectors going to point? Con or N? Is my acceleration vector going to point in the same direction or the opposite direction?
Opposite.
Why?
Because it's slowing down.
Beautiful. So then just come over here and go, oh, hey, I'm going to have a negative acceleration vector. That's it. That's all you have to do. Okay? That's it. So, boom. That's it. Do not make this complicated. Okay? Now, you're going to try and find the stopping distance. So now you're going to go back to that equation, and then you're going to go, oh, my stopping distance is going to be v squared minus v naught squared over 2a. And then you're going to use that acceleration. Gravity storm? Again?
It's because I hit my head, I'm telling you.
What'd you hit it on?
My car door. I was
How?
trying to open it. I don't know. And I'm in pain. Anyway.
I wonder, what kind of car are we doing
Yeah,
on
it
this?
doesn't matter. Okay. So here's the story. Let's roll that thought process that we just established on 29. Okay? If at going 20 kilometers per hour, you stop in 3 meters, if you double the velocity because it's v squared, what should happen to your distance? It should go up by a factor of 4. What's 3 times 4? There's your stopping distance.
Ooh.
Okay.
I got to test that. So you're
Charles?
right.
Oh,
What?
it's amazing.
Yeah.
Math. That happens. Okay.
I get 11.96.
On the multiple choice on the first 6, none of your answers should be C.
Yeah.
Okay? On the first questions, 1 through 6,
Oh,
none of your answers should be C.
Good.
Okay?
Should
Like that, Tyler?
Or our answer is D, question mark?
I'm just telling you, none of them are C. That's as good as you're gonna get.
Right now, man.
When you get to number 9, let's talk about the big idea on number 9. So your velocity time graph on number 9 should look something like this. You're starting here at 4 meters per second. Here you are at a half a second. Make sure that you have labeled the slope of the line. Clearly, what's the sign of the slope going to be? Positive or negative? Negative, right? So make sure you label the slope of the line. Now, when you get to D, you want to figure out how far the person slid. A couple of things you could do. You could just find the area underneath the velocity time graph because it's a triangle. Okay? You could do that. Now that you know the acceleration, you could use that equation if you wanted to. You could use distance equals 1/2 v plus v naught times time. You could do that. If you really wanted to get fancy, you could plug it into distance equals 1/2 at squared plus v naught time and plug in half a second. Okay? You can do that. You can literally use almost any equation that we have except for the first one to find that distance. It would make a horrible GPA. So that distance would make a very, very, very bad GPA. Okay? Now, let's talk about your answer to 9E.
9E?
9E.
Okay.
Okay. I've never heard someone get that excited about me talking about 9E.
I was just looking at that one.
Okay, so let's just talk big picture. At time 0, she's traveling at 4 meters per second. At 0.5 seconds, she has stopped. So at 0.3 seconds, what does your velocity have to be between? 4 and 0. Okay? It has to be somewhere between 4 and 0. Now, I didn't, but let's say that I had picked 0.25 seconds. If I had picked 0.25 seconds, what would her velocity have been? 2 meters per second, because that's when she's halfway slowed down. So I picked 0.3. So is your velocity going to be a little bit bigger than 2.5 or a little bit less than 2.5? A little bit less. So the only way you can really do that is just use v equals v naught plus at. You know your acceleration, you know your time. It's just a slope-intercept form. Remember, v naught is nothing but your y-intercept. Your acceleration is nothing but the slope of the line. The time is nothing more than your x values. Okay? So your answer to 9E would also make a horrible GPA. But a little bit better than the distance. Not much. On number 10, that acceleration, this is just the numeric value. Okay? Like the absolute value. On number 10, that acceleration should be between 160 and 180.
Okay.
Okay? I'm not saying it's positive or negative. I'm just telling you it's going to be somewhere between 160 and 180. The distance is going to be less than a meter.
You're talking about 10 and 8, right?
Yes. And the distance is going to be less than a meter.
Less than what?
Less than a meter.
Oh.
Okay. On 16, that acceleration, this is an ish, is around 10. And your time would make a not so good GPA.
Okay.
But better than the answer to 9.
All right.
Okay?
What?
Now, be very careful about what I'm about to say in terms of trying to get funny and cheeky. Your answer to 17 should be a little bit more than my age. Okay? And if anyone says 100, I'm going to beat you with
Wait, a little bit more than your age?
the answer to 17?
Yes. Is a little bit more than my age.
Negative 5.
How old are you?
I'm going to be 58 short.
Yes.
I got it right.
Brandon, what do you
I
have?
had 13.44. That's crazy.
Yeah, I think you're right.
A little bit older. Lions are on the day over.
Your answer to 18 would also make a horrible GPA.
That's alright. But better than the very first.
Yeah, I think, yeah.
Better than the distance.
Better.
About the same.
Yes. About the same as the velocity. Now, let's, on the questions out of the book, like on question 5, there are 3 things that I should look for and clearly see on your position time graph. You have 2 things going on. You have a fast car, a slow car, and when they pass. They're both traveling with constant velocity. So that should involve like a couple of sloping lines that should cross. Tell me which one is the faster, which one is the slower, and when they pass. Okay? So on number 5, I should see 2 or 3 things very clearly. Which one is the fast car, which one is the slow car, and the point at which the cars pass each other. Okay? Cool with that?
All right. Can you go over 11 real quick? Please.
I can't. So that's when you want to draw a velocity time graph to match what the position time graph is. Okay? So if you look on that position time graph, that's got, let me start with that. That position time graph goes doink, 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 doink. There's 0, this is a position time graph. So start with this. Connor A, what's the initial velocity of the object on 11? What's the initial velocity?
0.
Why?
Because the slope is 0.
Yeah, okay. So your velocity time graph for the first interval is going to do what? Just a horizontal line. That's it, because you're at rest. Okay? Now, what's going to happen here? What's going to be the sign of your velocity, positive or negative?
Positive.
Negative.
Negative.
Oh yeah, I looked at it.
Friday's going to be a long day.
Oh.
What's the slope of
Slope
this
is
line?
negative.
Positive or negative?
Negative.
So therefore the velocity is?
Negative.
Is it going to be a constant velocity?
No.
No.
Yes.
Yeah. Yeah. The
line,
yes.
I
I
know
this one. I got this one.
Maybe.
Oh, great, maybe. That got us to the moon. Is the slope the same?
Yes.
Is the velocity going to be the same?
Yes.
Did it change direction?
Yes.
Oh my God!
Because it's going down and it's going to 0. It's going down.
But it's a position time graph.
Oh, I do.
We're done.
I haven't seen.
You can physically probably see my hair turning more gray. Okay? I guarantee you, if you go back and look at this film and you compare it to when you started to where I ended up, my hair is going to be more gray.
I need to go back.
And it's going to say henna on it.
How much is the test worth?
60%.
How many points?
Oh, I don't know yet.
A lot.
A lot. Okay. So here's the story. Does this show constant velocity?
Yes.
Because the slope is the,
Same.
does it show change in direction?
No.
Why?
Because it's going the same way.
Yes. Does it cross the reference point?
Yeah.
Yes, so if like here's the reference point, all that's happening is you're going past the reference point. Okay, that's it. So how are you going to show a constant negative velocity? It's going to go something like this, right?
Yeah.
Cool.
Let's go.
Yay! Bingo. Okay, now, what's going to happen in this segment?
It's not moving.
So what's the line going to do?
Zero velocity.
Stay.
Gonna go back to
Back to zero.
0. What's gonna happen here?
It's going positive.
Positive velocity, how do you know?
Because
Positive constant slope.
Oh, that's a little difficult.
How are you gonna show that?
by going above.
Something like that. Okay,
What the?
Dylan?
It's okay if I do ask a backtrack question. I'm just confused on how v equals v original plus acceleration acceleration times
Whoa, whoa,
time.
whoa, I'm confused. What are you asking about?
Oh, the v equals v original plus a times t. How are you getting distance at that? I'm a little,
There is no distance. That has nothing to do with distance.
yeah, I saw.
Yeah, v equals v naught plus at, that has nothing to do with distance. Zero, zip, that has nothing to do with distance. No, that has nothing to do with distance.
I sorry, page numbers on here.
Now, distance equals 1/2 v plus v naught times time, that has to do with distance. But this has nothing to do with distance. Zero, zip, nothing. Okay. On 13,
There we go.
Thank God.
out of question 13, out of 11.
Yes. Oh my goodness.
That's what I got, I don't know if it's right.
Okay. Now, here's the story.
I might have thought something.
In this book, moving left is a negative slope or negative velocity. Moving to the right is positive, up is positive, down is negative. That's how this book defines the systems.
Right.
So on 13, it says moving the fastest. This is a position time graph. How are you going to find out when the object is moving fastest? What are you going to look for? The most shallow portion of the graph or the steepest portion of the graph? The steepest. Now, this is all in curving, so you got to view this from the perspective of tangent lines. Okay? So basically, when does the tangent line have its steepest slope? Okay? There you go. Now, on B, where it says is moving to the left. It's moving to the left when it has negative velocity. Okay? So at any point, if the tangent line has a negative slope, it's going to be moving to the left, because that means it's going to have a negative velocity. Okay? Does that help with that? Okay?
Wait, can you repeat B? Sorry.
So on B, when it's moving to the left, at any point, if the tangent line has a negative slope, it's going to be moving to the left.
Yeah, that's not a zero.
Okay?
He is still steeper.
So it's very possible for you to have more than one answer on that part on number
Do you
13.
need to include all the answers?
Huh?
Do we need to include all of them if there's more than one? Or, yes?
Okay. Anything else?
D.
On which one? 13D? Okay. If it's slowing down, what's going to be happening to the slopes of the line? Are they getting steeper or are they getting more shallow? Anything else? Now, let's talk about problem 20. Excuse me, question 20. So on question 20, that's a little bit of a different situation.
All right, we don't have.
Andy, Betty.
No, the area
Carl.
under the curve. The
Okay.
area under the curve.
Now, here's the story. This is a little bit different because they're all velocity time graphs, but up to this point in time, your velocity time graphs have always been what we call uniform acceleration. Okay? Always been a straight sloping line because we've always assumed that the force was the same, therefore we assume that the acceleration is the same. Okay? That's the assumption that we made. In reality, that isn't true. Like when you're driving your car, you don't press down on the gas pedal and then hold it there like the entire time. Okay? You vary the amount of force. But the whole point of why I picked this question was that it's the same idea as like a position time graph. So this is a velocity time graph. So if you were to draw a tangent line to a velocity time graph, what would that give you? Instead of instantaneous velocity, it would give you instantaneous acceleration. Okay? So the slope of these lines is going to give you instantaneous acceleration. Now, view this in terms of F equals ma. If you look at Andy's line, what's happening to the acceleration? It's increasing. So what's happening to the amount of force that's being applied? It's increasing. You're pressing down on the gas pedal harder. Okay? What's happening on B? What's happening to the acceleration? It's decreasing. So you initially press down on the gas pedal really hard, and then you're letting it off. Because you're approaching a constant velocity. Okay? So, again, understand what the slope represents. The slope represents acceleration. Okay? So, once you reach a horizontal line on a velocity time graph, what's the value of your acceleration? 0. Are you still moving?
Yes.
You're just not accelerating.
Yes.
Okay? So C is the only one that shows uniform acceleration. Now, on all three of these, what does the area underneath the line represent? Displacement. So when it asks for which one has the biggest displacement, what are you going to look for?
Largest area.
One of the biggest areas. Okay?
Wait, so I got both of them right? I got both of them. Get it now.
Oh!
I did, I don't know what you did.
The physics gods
What did
be
you get,
praised.
Charles?
So we got double B?
Yeah, you got it.
Okay.
Good.
Anything else? At all?
Oh, let me go through.
Alex?
How would I go at something? Thank you, Alex.
If it were me, if you look at the information that you're given, yeah. So if it were me, you know the acceleration, you know the initial velocity. Yeah. You know what time. Distance equals 1/2 AT squared plus V naught time. Okay. Once, twice, sold. So here's what I want. Listen to me very carefully. Green paper is going to go on the top. Now, some of you have multiple pages. Before you staple it,
Make sure there's an order.
make sure they're in order and make sure like number 1 is the first problem, okay? Don't randomly put these together and then, Burkamp will sort it out. No, Burkamp won't sort it out. Burkamp will grade it in the order that my answer key is in. And if you're start with number 5, I'm going to start grading with number 1, okay? So take a second, make sure that they're in order, and make sure that you have followed that format. Good? Give those handed in. Andrew, can you stop that camera, please?
Now, may I ask how